Okay, in this problem, we've got another rod going through a magnetic field. And so we know when we have a changing flux, so this is going to be our, let me just draw this area right, let's see if it'll draw. This is the area that we're talking about, that we're making a loop. So this is making a loop. This bar right here is moving to the right. So what's going to happen is this area is going to get bigger. And so when the area gets bigger, that means I'm going to have more flux. So I should have an induced current and an induced EMF or an induced voltage. So it says part A is find the magnitude of the induced EMF in the triangle. So remember that induced EMF is EMF is equal to a negative d phi dt, the magnetic flux dt, and magnetic flux is equal to magnetic field times the area. And so what we need to do is let's start with the area. So if we want to look at the area, this is the area that I'm interested in the red triangle, and it's going to become a bigger and bigger red triangle. It tells us that the rails form a 90-degree angle. So that means that this is a 90-degree angle. But it also means that this angle and this angle are 45 degrees, and this is a right angle. So what I want to do is I want to think about this bar moving to the right. So what's changing is this distance, right? Let me just erase some things. So this distance right here, this length is changing from here to here. And so as that changes, this length of the triangle is going to change, but also this height of the triangle is going to change. So what I'm going to do is, let's see, I'm going to look at, oops, I can't do that. Let's see, B times A. I want to look at just this part right here. And so I really want to just look at this triangle. And then whatever I find for this triangle, I'm going to double it for it to get this triangle. So my area of this triangle is area, let's call this 1. Area 1 is equal to, it's a triangle, so it's just 1/2 base times height. But now if I think about this triangle, so this is my triangle. Right angle, this is 45 degrees. I'm going to call this X and this Y. And so if I think about that, that's X and X, this is Y. If it's a 45-degree triangle, right triangle, that means that my X and Y are equal. So really my triangle becomes X and X. And so I'm going to say then that A1 is equal to 1/2 X squared. Right? Because I've got this one side and this one side, so base times height, 1/2 base times height. And the other thing is looking at this piece right here and it's moving to the right. I'm going to say that X is equal to V times T because this piece is moving to the right and it's moving with a velocity. In a certain amount of time, it's going to move further. And so that's my one side. And then since they're equal, I'm going to say that, that A1 is equal to 1/2 V squared T squared when I plug that in. And now the total area, right, so that's just area 1. The total area is going to be 2 times that. So A total is going to be 2 times A1. And so then that tells me that my area is going to equal V squared T squared. Great. All right, now what about my flux? So my flux, B is going to equal B times A. And if I plug that in, my B is equal to, right here, alpha T. Alpha is just a constant. And I'm going to plug in my area, and that's going to be V squared T squared. So I'm going to combine terms because I know the time is the thing I need to think about because that's going to be the variable that's changing. And that's what I'm going to be when I look at this equation for changing, or for my induced EMF, I need to differentiate with respect to T. So I'm just going to rewrite this as alpha V squared T to the third. Right, okay, so now I want to go to finding my EMF. So EMF is going to equal to a negative d phi dt, which is equal to a negative d dt of the magnetic field times the area, right? And they're both, now this phi is this new function. So we're going to have E is equal to a negative ddt of alpha v squared t cubed. And the other thing to know here is I have a constant velocity. So that's great. I don't have to worry about the velocity changing with time. So then E is going to equal, I'm going to pull out my constants, alpha v squared, and I'm just taking the derivative of t cubed. So that gives me 3t squared. So the derivative of t cubed is just 3t squared. So the induced EMF is negative 3 alpha v squared t squared. So move on to the next one. So this is just part B. I just added the part B, sketch the plot of the magnitude. So it's asking me for the magnitude. So notice that from the last slide, our E is equal to a negative 3 alpha v squared t squared, but I'm doing the magnitude. So I'm just going to make that a positive. And now if I think about this, this part right here is just a constant. So really I just have c times t squared, just some constant. You know, I can calculate what that is times t squared. And so this just looks like a parabola. So, and there's no constant here in the equation, so I'm just going to start at 0 and draw a parabola. And so that's part B, and then it says, what is the direction of the induced current in the triangle? So so if I think about this, my area is increasing and my magnetic field is also increasing. So so what that tells me then is if they're both increasing, then I want to oppose it, right? So I've got this triangle like this, right? And what's happening is this triangle has more and more of the magnetic field going into the page. So the current, the induced current in this loop is going to want to oppose that. So it's going to want to create, and it's going to say, hey, I need to create some out of the page B field. So in order to get out of the page B field, I point my finger, my thumb in the direction of the out of the page for the B field, and my fingers curl around to show me where the current goes. So then my induced current, so I induced, is equal to counterclockwise. Okay, part C, find the magnitude of the induced EMF at this time, given alpha, and then find the power dissipated, given a resistance. Okay, so we've got our E is equal to 3, so magnitude 3 alpha v squared t squared, and so I'm going to plug in 3, alpha is equal to 1. I'm not going to add units here, just to get through the video. V is equal to 1, and T is equal to 2. So that tells me that the magnitude is equal to 6 volts. And then we need to find the power dissipated. So the power is equal to V. One of the equations is V squared over R, and I'm given V, right? So my V is really my induced voltage. So this is going to be my induced voltage over R. They give me R, so that's a good equation to use. So I'm going to say 6 squared over 72 ohms, and that's going to be 36 over 72. So P is going to be equal to half a watt. And now this last part, the bonus, is asking me instead of the magnetic field, if instead the magnetic field decreases, and so now my B is alpha over T squared, which way will the current flow? So let's look at so this is bonus. So if we look at our area, or our flux, we're going to have B times A, so B times A. And if we plug in, we're going to have B is alpha over T squared, and area is V squared T squared. So what happens to my flux is that my T squareds cancel. So I'm just going to have alpha V squared. So what that means is my magnetic field is decreasing at the same rate that my area is increasing. So this is a constant. So phi is a constant. Doesn't depend on T. So that means I will have, if the if there's no change in the flux, that tells me that my that there is no current. So there's going to be no current, no induced current. Go. I did it again. Induced current.